Okay, triple integration land. So here we really, again, have to think one more dimension. So that's hard to do. It's hard to go from 3D to 4D, but we're going to do it today. For a function, what we're looking at now is something that's dependent on x, y, and z. Z is no longer the dependent variable. It's one of the input variables. And so we can't even really graph this like we've been in the 3 space. So an example that I think is a little bit helps conceptualize this is imagine that your location x, y, z in 3 space, you know, that's like our input now to our variable in triple integral land. And think about something like temperature. We have some sort of heating element that's throwing heat out, and we have circulation in the room, heat rises. So where the particular temperature could be dependent on the XYZ location. And it wouldn't be something that could be reduced down potentially to just the XY plane or whatever. And so that temperature is kind of a invisible thing that could be a function of the XYZ location. There are ways to graphically represent this in a little more discrete nature, like balloons in XY space, like having a magnitude represented at a point with kind of a sphere that shows magnitude. But in general, it's hard to represent that. So anyway, now the mindset is we have this function that's a function of x, y, and z, and then our domain becomes a box, and it has volume, and it's a solid. So what we have been graphing is maybe something that we're trying to represent, like the volume underneath the surface, has now become our domain. And then this thing that we're trying to integrate that is this 4th dimension is something that we don't even see, these problems. I'm not going to, we don't even attempt to visually display that. So that's an important point moving forward, because for the double integrals, we were trying to just find volumes of these things, which are now our domain. So anyway, moving forward now, here are ideal kind of simple domain, which we're going to call E now, or B, depending on, so B is sort of like R, the rectangular 2D space domain, the easy one, has now become B, and it's a box that's a solid, so it's not an empty box, it's a solid, it's stuffed with things or whatever. It's a solid. And it has 3 dimensions, delta y, delta x, and delta z. And so that's what we're integrating over. So a lot of things are similar to our double integral. And we're going to talk about the physical significance of this after your test, actually. So right now we're just going to focus on how do you evaluate that integral, and just kind of go on mechanics and get some comfort up. And then also it'll kind of help with what you're doing in double integrals, it turns out. Okay, so we got a triple integral over B, which is again like the R in 2D, and we got our big B, and that is representing a rectangular prism or box that's solid. It looks not so bad. We got 8x, y, z. We're given our bounds. It goes x, y, z, as you'd expect. So by Fubini's theorem, there's one for our triple integrals. We can do this in any order we want. Really, for this one, it doesn't really matter. One thing to notice is if you have a variable bound, or not variable bound. If you have a constant bound that's 0, often that simplifies things. So you might want to do that first, because then you start with something simpler and have less plugging in, instead of plugging some stuff in and then, oh, it's 0 now and I did that work. But really doesn't matter too much. So just like you expect, we do our innermost set first. I chose to do my z first, and so I did that, which just amounted to having 1/2 c squared and carrying along all the other stuff as a constant out front. Then we plug in, and now we got a double integral. So now with this double integral, that's what you will have on your test next week. And so these triple integrals, kind of like with the single variable situation, remember we did a double integral and it was kind of weird at first to do the first set of integration, and then it became a Calc 1 integral, right? So now with the triple integrals, we're going to do this weird new thing for our first integration, and then it becomes a double integral, which is just a double integral from before, and then it becomes a Calc 1 integral. Okay. So the rest of this, you know, go ahead and go through the motions. This one really was not too bad, but as you can imagine with the triple integral, just having to do those 3 integrations and plug in that extra time can be quite lengthy. So maybe some of you noticed or were thinking, is there a shortcut for this? Can I do the shortcut? I can do Fubini. Can I do the shortcut? Yes, you can. So when you have the numbers here in for your integration bounds, notice how they're all numbers here? Then it's kind of a free-for-all, and I can just go ahead and grab the stuff that's an x and do an integral with respect to x because it's multiplying here, and totally do that. And it's worth your while because it saves a lot of time, it turns out, especially with a triple integral. So here, notice I put all my y stuff together, x and z. I can pull up my constant. Then I just do each of these easy single integrations, and then it was less work. Yep.
So you can only do that with multiplication, though, correct?
Yes, only with multiplication. If it's plus, you can split it up, but it's still the double integral. And then another point, when you have variable bounds, then you can't just be like switching stuff or breaking it up. So whenever you have variable bounds, they're not just numbers. You got to be careful. You can't, those things don't necessarily apply. Most times they don't. I'm going to gloss over this really quickly. For the double integrals, we didn't go over the cases. Here, I had kind of contemplated not doing that, but I don't want to spend a lot of energy on this. Your book goes over type 1, type 2, and type 3. Type 1 has 2 subtypes of the type of triple integrals you can set up when you have variable bounds. I would like to take a more kind of organic approach like we did with the double integrals and seeing what makes sense to have variable bounds. And it's more obvious for the problems I'm going to give you because these could get really nasty really quick. So they're going to be kind of easier just because it's hard anyway. So with that being said, don't spend too much energy on this because as general cases I think it's kind of hard to see even what's going on or what would make sense to do. But just kind of what I want you to get from this is notice that when we have variable bounds, we have lots of options here. Instead of having 2 cases, we have 3 because we could do the integration with respect to x first, y, or z. What's going to feel more natural is with respect to z. That's going to feel more natural to do first. And so that's what you're going to kind of look for. And then another thing that can happen with the subtypes 1 and 2 here is that then maybe when you're done with that integral or you've taken care of that innermost set integral, remember what I said about it becomes a double integral? In the double integral you had to graph the domain, D. Same thing here. So once you take care of the variable bounds with respect to 2 other variables, so let's say it's z is dependent on x and y, then that's the one that you have to set in the innermost because it depends on x and y. And it's going to have variable bounds associated with that. So once you take care of that, then the rest of that integral is going to be the double integral, and you treat it the same. And the first thing you're supposed to do for the double integral is set up the domain. And it's going to be with whatever is left over. So for this natural case of doing z as the innermost set of the triple integral, it's going to be in the xy plane. So that's what all these pictures are supposed to be illustrating. So I put them out there just to kind of give you a heads up of what to expect, but definitely I would suggest you don't memorize them, especially not right now, but just putting out the possibilities there. All right, so I'm not going to get to this example, so I'll stop here and then to be continued.